I briefly mentioned overfitting. Let me talk a little bit more about that and what does that mean, okay? Because this is really important when you work with datasets and you try to train and test. Let's look again and this set of points. The blue line is a degree 15 polynomial. Okay, so in fact, if you look, at how well we are doing, we are probably doing really well with this fit. Okay, the errors on the training data are really small. I mean, look at the distance between the blue dots and the blue line. It's really small. But think what happens if you get a new point whose value is around 2, whose value is x equals 1.8 or something like that. Okay, the y value is going to be completely off the charts just because of the degree polynomial that we have used to fit. Okay. Imagine that, alternatively, we propose the fit on the right-hand side, this other fit. Okay, this other fit is probably a better fit for new data. So when a new data point comes, say we have the 1.8 value on the x-axis, if we have 1.8 on the x-axis here, the prediction is going to be kind of correct. Whereas here with the polynomial, the prediction is going to be off charts. Okay, so what overfitting means is that in this case, this model is going to give you a really small error, a really small empirical error, but it's going to do terribly bad during the prediction. Whereas this model here is going to give you a small also training error. Maybe even the error is going to be a little bit larger than the degree 15 polynomial, but during testing is going to give you better results. So this is something that you want to avoid, overfitting your models. In order to minimize the risk in the new sample points, okay, so when we have a new point that we're going to use for the prediction, to minimize that risk, it depends on 3 different factors. Okay, so let's try to unpack a little bit the meaning of bias and variance. Bias is basically the difference between the values predicted by our model and the actual values, whereas variance represents the variability of the model predictions. So what's the spread of the different values that we have predicted? If you look to the left-hand side, the plot explores the 4 different combinations between high bias, low variance, and high variance, or low bias and low variance and high variance. Those are the 4 different scenarios where we can evaluate our models. And on the top left-hand side, we have the setting with a high bias but a low variance, meaning that the difference between the truth values, which is the circle at the center, and the actual predicted values is really high. That's a high bias. But the values are really similar to each other. There's a low variance. Okay, and that setting is what we could define as underfitting. This is basically a model that doesn't predict well any of the values that we want to predict. Okay, it's not sufficiently trained. Basically, in other words, high bias represents a model that does a really poor job at prediction, that has really poor performance at the prediction task that it was trained to do. On the other hand, if you look at the bottom right corner, the low bias with high variance represents the opposite scenario, where the values are distributed around the truth value, so bias is not high. However, the spread of those values is really large, meaning that the values that are predicted are all over the place. So there's really not a definite trend that was found by the model. This setting, the high variance setting, basically what happens here is that the model is trained to adapt very well to the training data, but that means that if the training data contains noise, that noise is going to be incorporated as part of the model, okay? And as a result, the model is overfitted, meaning that the model is going to do really well for training, but it's going to perform badly during prediction, okay? Okay, so let's look a little bit more into this. So this plot is showing a similar analysis of the bias variance trade-off, but with a different representation. In this case, on the x-axis, we have model complexity, and on the y-axis, we have the squared error of the model, the prediction error. And we are plotting the overall prediction error, which is composed of a bias error and a variance error. As you can see here, if we look on the left-hand side, the underfitting side, you see that when the model complexity is low, Okay, what happens basically is that we have a very small number, for example, of independent variables in our prediction. What's going to happen is that the model is going to have a high bias related error. Okay, so basically the model is not trained well, and that results in a high prediction error, while the variance might be small. Okay, meaning that the points are in the same neighborhood. On the opposite side, you have models in which basically the model complexity is much higher. We have many more independent variables, okay? But in that case, because of that variance, the variance is really high, and so it's much harder to model because of that complexity. And in that case, we will incur in high variance errors. Basically, we are trying to compute a really hard model, and we are highly probably incorporating noise within that model. And so because that model is a really complex model, the variance error will be high, as opposed to the bias error that will be low, because bias error is basically just the difference between predicted values and actual values. So we might be doing really well. We will be doing really well at you know, predicting those values during training. And so, that component is overfitting. And what this plot is telling us that we are in reality looking for a sweet spot in between those different scenarios, in between the high bias versus the high variance scenario. And that sweet spot is going to be the spot where the prediction error is the lowest and where we are neither underfitting nor overfitting. So let's look at an example and let's look how we can solve it with regularization. If you think about gene expression, so gene expression measures the level at which a given gene determines the synthesis of a protein. Okay? Can we use gene expression to determine a type of cancer, to determine survival time? If we look into, different gene expressions, how's that going to be predictive of your survival time? In this case, the problem that we are facing is that in reality, only a small set of genes are going to affect the survival time. Okay, so the type of cancer or survival rate is going to depend probably on just a very small number of genes. However, what in reality happens is that we have thousands of genes for a very small number of patients. So the number of genes, the number of features that we have is much larger than the number of samples that we have. Okay, we're going to have, say, 100 patients, but we're going to have thousands of genes per patient. So this is a problem in which we have for each patient a lot of features. Okay, so it's going to be a potential problem in terms of overfitting. In fact, again, this is just a graphical representation. So for each patient, we're going to have thousands of features, but we have a very small number of patients. So we need to make sure that we focus on the features that are going to be highly predictive of our outcome. In this case, survival rate or type of cancer. Okay, not all features are going to be predictive. So which ones are the important ones? That's what we want to look into. So if we just simply take all the features, all the genes, okay, and try to train on that, we're probably going to overfit. We have too many features, too few patients. We'll overfit the model, and when we get a new patient, the prediction is going to be terribly bad. So the solution to that is basically try to assign really small or zero coefficients to many of the genes there, to many of the features that we have, because probably they won't be important. And that's where regularization comes in. Okay, regularization is a method used to prevent overfitting by penalizing models with extreme parameter values. Okay, so basically to control variance, we regularize the coefficients. We regularize how much the coefficient for each of the predictive features, for each of the independent features grows. Remember that when we are looking for the best fit for a regression, we are always looking to minimize the error. We are minimizing the empirical risk. Okay? Minimizing the empirical risk, the function that we've seen so far is this one. Okay, the one within the square. So we are trying to minimize the difference between the actual value, the y value, and the predicted value. Okay, the beta xi. Is the squared difference. That's a traditional way that we've used to compute the best fit. So we basically minimize the distance, and that's our model. However, that model, as we have explained, has risks of overfitting. So that distance might be incredibly small, but then when a new sample comes in, we perform poorly. So what regularization does is that it adds basically a set of parameters or a set of penalties that are going to penalize different features. So some of the features in the model are going to be penalized, meaning that some of the coefficients in the model are going to be 0 or almost 0. So in this case, finding the best fit is not only going to be finding the best beta or theta values of our model, but it's also going to be finding the best lambda. The lambda that will find that sweet spot that's going to that's going to highly minimize the impact of some features that are not that predictive of the dependent variable. We're going to see two different types of regressions based on their penalty functions. Ridge regression, which is also known as L2 regression, uses a squared penalty. So as you can see there, the penalty function is the squared value of the beta of the coefficients. And the lasso regression, L1 regression, it uses an absolute value penalty. So it uses the absolute value of the coefficients. Okay. How do each of those work? So Ridge is going to assign many coefficients close to 0. None of them are going to be 0, almost none of them are going to be 0. So what happens is that this model is good when we know that a large number of the coefficients play a role, but some of them are much more important than others. So what Ridge is good at doing is highlighting which ones are highly important. Whereas basically Lasso assigns many coefficients to 0 value. So it's literally eliminating those coefficients. Okay. And in this case, the models that we generate using Lasso are much easily interpretable because, of course, we have fewer estimators. But those models tend to work well only when we know that, a very small number of estimators are going to be important with respect to the predictive class. So in the gene example that we were explaining before, depending on the type of cancer that we want to predict, the number of genes is going to be really small. So probably Lasso would work better because it's going to give 0 values to many of the other genes and focus just on the ones that are highly predictive. And the model is going to be, much more interpretable. In the end, and again, what I'm explaining here is something that you will not be asked to do, but rather I would like you to understand how this, is worked by R or by any other machine learning packages trying to do this type of regressions. When we use a lasso or a Ridge regression, as I was saying, we also need to approximate the value of lambda. So it's two approximations. First, the value of the theta values and then the lambda. So similarly to the polynomial regression, we are going to have two different sets. Okay, one set is going to be used to basically fit the theta values, and the other set is going to be used to approximate the lambda value for the penalization. The way this is done is typically through a k-fold cross-validation. What this means is you take the training data and you divide it into k different folds, k different subsets. And then you use k minus 1, okay, you fit the model with k minus 1 subsets, and you basically compute, a model with those subsets, and then you compute the cross-validation error with the last fold that you have. So k minus 1 folds are used to fit the model, to approximate the coefficients, and then the kth fold is used as a cross-validation fold to approximate the lambda value. And of course, the lambda value that is selected is the one that has the minimum error during the cross-validation. This is exactly, again, the same philosophy, okay, that we have explained with linear regressions, with polynomial regressions, okay. We need to have a training and a cross-validation set to estimate the different values and avoid overfitting and to make sure that, we approximate well each of the parameters that we are working with. Let's stop here, and next we'll look into exercises with R. Let's take a break.